Hey guys, welcome back to my YouTube channel. So as promised, this is a teaser for the CAPE Chemistry Unit 2 classes. There's still space, so you can join. Contact me.
Start over. So let me start over. So gravimetric analysis is a form of quantitative analysis in chemistry. And and when you say quantitative, it means that you're going to assign numerical value to the analysis that you have worked out, or that because like in quantitative analysis, you don't assign numerical values to what you have analyzed. It's
in what
basically
in what you don't in what you don't what you say in what
you're
don't
really
you
low.
sorry what did you say? You said you don't apply numerical values in one of those analysis. Which one did you say?
In quantitative analysis.
Quantitative?
Yes,
You sure
quantitative
it's
analysis.
quantitative?
Yeah, qualitative. No, in qualitative, sorry, in qualitative analysis, sorry.
No problem. Remember, here's where you need
Sometimes, sometimes we stop it 4 words and quali,
that's fine.
quality, and then quantity. Quantity, qualitative, yeah. So basically, you have two forms of quantitative analysis. One of those, what we use, or basically focus on in chemistry, you have the gravimetric analysis, and then you have the other one. They have the volumetric analysis, or you can just call it the trigonometric analysis, right?
The what?
In gravimetric,
The what? The you said gravimetric and what?
trigonometric, or I just
Or
say volumetric.
titrometric?
Huh?
Titrometric?
That's how you say it? Titrometric?
Mm-hmm, mm-hmm. Like
Okay.
titration.
Yeah. Oh yeah, true. Like yeah. Ti- Come again, please.
Titrometric.
You're really low again.
Titrometric.
Yes, titrometric analysis or gravimetric analysis. In titrometric analysis, what we focus on is the volume, and in gravimetric analysis, what we focus on is the mass. And the whole principle behind gravimetric analysis is that you are weighing a compound of its known chemical composition, so you know exactly what's in the compound. So for example, let us say you have copper sulfate, you have the hydrated salt copper sulfate. So you know that what the chemical composition of copper sulfate is copper, of course. You have you have sulfur in it, and you have oxygen, and you have water, of course, because it's a hydrated salt. So you know from the get-go that's the chemical composition. So when you weigh that compound now, and you know its chemical composition, you're basically able to determine the amount of one of the substances that are present in the compound. So when you carry out the gravimetric analysis of the hydrated salt, copper, for example, copper sulfate, and let us say you wanted to find the amount of water within that compound. So you know from the get-go that you're going to be weighing it, and you're going to be carrying out the principle. So at the end of the day, you are going to be finding the mass or the amount of water within that hydrated salt, copper sulfate, for example. No.
You have more?
Yeah, I have more. So now, when you're carrying out the gravimetric analysis, there are certain stuff that you're going to have to be doing. You're going to have to be doing preliminary treatment in some cases, and this is basically where you're basically adjusting the pH of the substance. It all depends on what you're doing. And then you have the task of making that, what's that word, of forming a precipitate from that compound that you wanted to do, that you want to find the mass of. And when you're trying to create a precipitate or make a precipitate of the compound, you're basically going to be using a sinter glass base, a filter crucible, and one of those conical flasks that has a suction pump with it. You don't use a normal filter paper, and you don't use a normal filter paper with the funnel. You know, the one that you're used to. Well, what I'm used to, like we're using grade 11 and all that, when we were basically just trying to normally filtrate something,
Yeah.
filter something.
Yeah, I know what you're talking about.
Yeah, so yeah, good. So you know me, I said. So you don't use that one. You're basically going to be using the filter crucible, the sinter glass base, and a conical flask, conical flask with the suction pump on it. That's the setup you're going to be using.
What's the funnel called?
The funnel is called the funnel. The type of funnel we're going to be using is a filter crucible. That's the name of the funnel.
Oh,
And in that filter crucible, you have a sinter glass base in it.
Buchner's funnel, okay?
Oh, okay.
BU with 2 dots at the top, CHNER.
Say it again, please.
BU with 2 dots
Thank
at the top of the U,
Yeah.
CHNER.
Okay, okay, thank you. Thank you very much.
Question. Why do we use the sinter glass crucible or just a crucible instead of, say, a test tube for heating?
Because the crucible, it is able to what the hell? Wait 1 second. Yes, it's able to withstand temperatures up to 200 degrees Celsius. The test tube, you can't do that with it. It can't withstand temperatures that high.
Yeah, it will break. Very good. Okay, so
Yeah. So after you have carried out the precipitation process using that the Brochner apparatus setup, right? That's the word.
question?
That's how you pronounce the word, the B word.
Buchner or Buchner?
Yeah, the buttoner. What would you call the apparatus setup? Well, I'm gonna say the apparatus setup. So after you carry out the precipitation process with that apparatus setup, you are now going to be washing the precipitate, and you're going to be washing the precipitate with distilled water, but you don't want to wash it for too long. You're just going to basically rinse it off, and you're basically just going to rinse it off because you don't want any of the precipitate to redissolve or anything like that. You just want to wash it off in order to get up any amount of the impurities or what you can manage from taking out. Then no, you're going to be drying that precipitate. You're going to be drying the precipitate, and there are several different ways of how you can dry the precipitate. You could use an oven, and you could use an oven for that for one of the ways. Another way you could dry it is basically just putting the precipitate in a crucible with its lid, and then no over a Bunsen burner and drying it for that amount of time. So that's one of the ways you can either dry it. And yeah, and after that, no, after you have created after after you have treated it, you have created you have created the precipitate, you have filtered it, and you have washed it and dried it. You're now able to carry out the calculations for you to determine the amount of substance in the chemical compound that you had started out with.
All right, very good. Um, you have a tiny misconception with the explanations, though. I've been waiting for you to like finish so I can mention it. You finish?
Yeah, man.
All right. You said that you'd know, like, if we want to find out how much like barium chloride is in the thingy, we would in the sample, we would know exactly the mass of the barium chloride, right? That's
I
not
realize that
next.
it's a mistake. You're only going to be able to find the amount of one of the substances. You can't find everything, but only one of the masses for the compound.
Okay, yeah, that's the reason why we use gravimetric analysis actually, because we can't, like, for some things you will get impure substances, and with that impure substance you will know that it's like barium chloride and something else, right? That
Yeah.
makes up the mass of your sample. So what you need to do now is make not mix it but react it with something else that you would get a precipitate, so you can weigh that precipitate and do some maths, right?
Yeah.
So yeah, so you ready
How
now?
the how the volatilization work though?
Give me a sec. All right, so I think the banging has stopped. So all right, so the question that you asked for volatilization gravimetry, it's like what you did in your lab, the lab that we went through the other day.
You
um
mean the copper sulfate one? That's the volatilization
yeah,
one? So
yeah.
wait, what is the normal? What's the precipitate one then?
When you do the precipitation gravimetry, you will get
Uh-huh.
a precipitate, as it says, right? You mix
Yeah, man.
two things to get a precipitate, and then you dry the solid. For volatilization, though, the separation, what do you call it? The separation technique is used
Mm-hmm.
is basically by heating or by chemical decomposition. Seeing that the copper sulfate, it was already insoluble, right?
Yeah.
So
Mm-hmm.
you didn't mix it with anything to form a precipitate, right?
No, you just add, you just added heat to it.
To
You
remove
just
the
added
water
heat.
of crystallization. See the
Oh,
difference
so that's
now?
volatilization. Why
Yeah.
I ask is when I was researching it, like I wasn't seeing a clear difference between the volatilization method and the precipitation method. That's why I may ask. I mean, never see one clear distinction between two of them. So now
Oh,
you said the
okay.
precipitation method, you have to. So this means it would work really well with like sulfates, like for example barium sulfate, because you know those readily make precipitates when you mix them, when you combine them with certain other stuff. So you say you get the precipitate, and then no, you're going to have to basically carry out the filtration. You're going to be using the apparatus that I mentioned earlier on before, right?
Yes, what is it called? Miss
Bouchner?
Buchner?
Butner, yes, the Butner apparatus setup. We're
Yeah.
going to be using that, right?
Mm-hmm.
Okay, so you use the apparatus setup. I have a question though. When I was looking in the book, I was saying I saw the Butner apparatus as a normal one, what we use like in grade 11.
Mm-mm. No, miss. It look
So
like,
then,
but I think it's best you look at lab experiments on YouTube doing it,
yeah,
because the book, the way it's drawn in the book, it kind of looks like the normal filter funnel, and except for the fact that the funnel is a bit square or rectangular shaped, as opposed
yeah,
to the normal filter funnel being like triangular shaped, right, or
yeah,
conical
uh-huh,
shaped.
yeah.
But that's the most like significant or difference when you look at the book. But it's easy to
And the
mistake
conical
it.
flags of
So it's best if you
walking.
look at like a lab experiment, because you'll see a lot of differences. You'll see holes in the funnel, right?
Uh-huh,
In the Buchner's funnel.
uh-huh.
And usually they use a Buchner's flask as well instead of a conical flask, but some people use the
Oh,
conical flask. The difference now with the Buchner's flask is that it has like a little tubing in it where you can attach a suction tube
oh,
to help with
oh, yeah,
with
I saw that, I saw that.
yeah. So yeah.
Oh, oh, 1 second, 1 second.
Mm-hmm.
Alright, alright.
All right, so you're ready to do some calculations, everything there clear?
Yes, so basically the main difference is that when you're doing volatilization, I think the volatilization method will work really well with hydrated salt, because then all you're going to be doing is just removing the water from it using like heat, right?
Ben what?
I was asking if the volatilization method will work really well with hydrated salts, because all you're doing is just removing the water from it.
Yeah. Yeah, yeah.
Which other substances, which other chemical compounds can the method be applied to the volatilization method?
Just anything with water of crystallization, really.
So hydrated salt
So
stuff.
so washing soda, washing soda has 10 water molecules. The
Okay.
copper sulfate has 5.
Mm-hmm.
Like I don't think I know anymore. Oh, global salt,
What's the salt?
something sulfate. It's 10.
Oh,
10 it
many things say sulfate that only use precipitate. Okay,
um
okay.
the thing borax that they
I
always
know
say in
what?
physical, right?
Mm-hmm.
The formula that everybody know except me. That's sad. Dot 10 H2O. That means it
Yeah.
has 10 water molecules, so that's the water of crystallization for that. I don't think I know anymore off the top of my head. I just
And
know
then,
those.
okay, thank you. And then you would use the precipitation method and stuff like that. You know for sure going to form a precipitate. Like for example, some sulfates, the SO4, like some iodides, right? Like calcium, potassium iodide. Yeah, the iodides, and some chlorides. Not true.
Yeah.
So sulfates, iodides, and some chlorides. Okay, so that's what you're going to use the precipitation method for, and everything is basically the same for the hydrated salt. No, hydrated salt. I forgot the heat. I forgot the heat to it. You're not really focused on precipitating anything. You just go try. Yeah, just go try work on spaghetti. Apply the heat voltization method in the what you call it, the precipitation method. You have to go carry out the buttoner. You have to go use the buttoner apparatus, and you're going to have to heat it like you would in the volatilization method. Right.
Yeah, yeah.
Okay. I think I'm on track now. We can do the calculations now.
All right, great. So let's start.
Yes, me.
That's my Zoom. All right, you seen the question, right?
If something is blocking it.
Still?
Yeah, they're gone. They're gone. Yeah, they're here. They're gone.
All right. So first of all, you're hearing me properly, right?
Yes, me.
All
Wait,
right,
let
great.
me bring up the periodic table thingy that I can easily tell the masses when they ask me for them. The periodic table. Alright, so it's up. It's up now.
No, I don't want to rate your app. It's very good, but I don't want to.
What happened?
This thing always asking me to rate the app. I don't want to rate it. That take a lot. Ready?
Yeah, it took a lot of time for it.
All right, so this says when 0.611 grams of hydrated barium chloride is heated to constant mass. Remember, to constant mass is important
Why is that important?
because then you'd know that all the water of crystallization has been removed.
Oh, so that's what that means. Okay, thank you. I didn't know that. Okay, thank you.
Yes. I told you this the other night when you were doing your lab and you wrote it as a source of error because you stopped at the 5th heating, but then you didn't get a constant mass or anything close to constant, right? Yes, I
Oh,
see that.
that.
Mm-hmm.
Oh yeah, you explain. Yeah, true. You explain, but you use a term that I wasn't familiar with the term. I know that I understand the concept, but the term I didn't remember. I didn't remember this the term. But I know the concept though.
Okay, that's great. So, I'm so sorry. When you get the constant mass, it was 0.52 grams of residue, right? So that means that what would be the residue?
The residue it would be the anhydrous salt, basically, and the anhydrous barium sulfate, barium chloride. I'm so used to saying barium sulfate, barium chloride.
Yeah, very good. I know they want you to deduce the formula of barium chloride, right? Hello?
Yeah, man, I'm here. They want me to find the formula. So basically, they want me to find how much water was in the hydrated barium chloride.
Very good. So whenever you're doing questions like this, moles specifically, because remember I taught you moles based on understanding and not based on a formula, right?
Yes, beautiful.
So
Yeah.
that so that it wouldn't be so confusing. All right. So what you want to do is ask yourself, what do I know and what do I need to find out, right?
Okay.
What do we know? We know that 0.61 grams of hydrated barium chloride, right, was heated,
Yes.
right?
Yes.
So we know that BaCl2 dot XH2O was heated, right?
Yes, we know that.
So Q. And what would be formed?
We know that we are going to form BaCl. BaCl. That's going to be what? The solid? That's going to be solid plus the dot XH2O. That's going to be in the form of a gas.
All right, tell me, Miss,
Yes, ma'am.
what's missing from your equation here?
State symbols.
Yep, and what else?
Hmm. I'm coming. BaCl2. That should be a BaCl2 over there. So
Very good.
yeah, everything else seems to be okay. So state symbols. Yeah, the dot XH2O should be gas. The
Wait,
BaCl2
wait. What dot H2O? The BaCl2 dot H2O should be what?
that should be aqueous. That one should be aqueous. What you start off with should be aqueous. BaCl2 dot XH2O. It should be aqueous.
Okay.
And then BaCl2, it should be solid. And then the XH2O should be gas. You're going to lose it as a volatile. It's going to be volatile. So you're going to lose it as a gas. So we know that we heated 0.611 grams of BaCl2 XH2O. That's what we know, and we know that 0.521 grams of what the the BaCl2 as the anhydrous salt was formed, and we need to find out how much molecules of water are in BaCl2.
So what would we find next?
Okay, what we would find next?
Mm-hmm.
Alright, now. Alright, we're going to have to find out how many moles. I get to that for. We're going to have to find out how many moles are in the hydrated salt BaCl2 dot XH2O. I'm going to find out how many moles are in the BaCl2, well, the grams. So we're going to find out how many moles are in 0.611 grams of the hydrated salt BaCl2 dot XH2O. And we're going to have to find out how many moles are in the 0.521 grams of the anhydrous salt BaCl2.
How would we do that? We don't know how many water molecules are there, so we wouldn't know how much, to.
Yeah, that's true. So we're going to basically just be using BaCl2 right now. Cause
Which
we don't know
one?
how many the anhydrous salt.
All right. But remember now, we're looking for how much water is in this, right?
Yes, that's true. How many
How would we do that? How would we find that?
I would find it. Oh,
Mm-hmm.
I know you're gonna have to use a mole ratio or something at the end of the day to find out how many molecules of water are in it.
Mole ratio of what? There are only two choices here. So think it out. Mole ratio of what?
The mole ratio of. I see that I have the barium chloride. I could use the mole ratio of the barium chloride.
So ratio deals with comparison. You have to compare it with something.
Alright, I have to compare it. So I'm going to use the mole ratio of I'm going to compare the mole ratio that I get for the barium chloride to I don't have a choice. I'm going to have to use this over here. So the dehydrated salt. But I don't know how many
Yeah, you're going to
moles.
need to use it, but how would you use it? Remember, you're using it to your advantage to find out something else that you need. So what
Alright.
basically that 0.611 grams, right? That is the mass
Mm-hmm.
of what?
That's the mass of dehydrated barium chloride,
Which
the
means
salt.
that it's the mass of, if it's hydrated, meaning, tell me
It
what
has
that means.
water, so it has water. It would have to contain the amount of water in it as well.
Exactly. So you're telling me that barium chloride dot BaCl2 dot XH2O is the mass of barium chloride and some amount of water, correct?
Correct. Yes.
So the 0.521 grams there, what is it telling me there? What's the mass? Which mass is that telling me?
That's without water.
Exactly. So how can we use these two values to our advantage?
We could subtract them, and if we subtract them, you're going to figure out how much water was lost.
Very good. So do that. Tell me what you get.
I'm coming.
Mhm.
0.611 minus 0.521 is equal to 0.09. 0.09.
All right, very good. So we know that the mass of water loss was 0.09 grams, right?
Yes, that. Yeah, Camille, give me a quick sec. Stop recording for a second. I'm going to write off a question properly and something. Alright, now. Hmm. Have me a talk? Um.
Oh, I'm sorry, my mic was muted.
Okay.
This happens to me so often, it's not even funny. All right, I'm saying that we know the mass of barium chloride and we know the mass of water. What are we going to do next?
Alright, now you're going to basically find up the amount of moles in each mass of the you're going to be finding the amount of moles in each mass that you currently know. So you're going to be finding how many moles are in 0.521 grams of BaCl2, and you're going to be finding how many moles are in 0.09 grams of XH2O.
All right, great. So tell me, how would you do that? Please leave. Let's
Okay.
deal with BaCl2 first.
All right, now you're basically going to be setting up a what you call it, a relationship, a proportionality relationship. So
Okay.
first of all, we're going to have to find out the molar mass of BaCl2. Okay, let me bring up that beautiful periodic table of mine. So BaCl2, where's barium? Barium is 56, so it's going to be 137.327. How many should we use, Cameo? Everything are just four significant figures. Or
I use
three.
4 sig.
Okay. So then the moles of barium is equal to 137.3. Chloride, a beautiful
Chlorine.
hazel. Chlorine. Why do I always say that? Chlorine is going to be to four significant figure is going to be 35.45, and that's going to be twice the value. So yeah, two of them. You're going to have, what is it? Let me just say a lot of 35.45 times 2. Alright, 70.9.
Eh?
Yeah. You're going to
What
have
you say?
70. Two chlorides. I use four significant figures for the
Oh, I thought
chlorides.
that was the whole
For
thing
the
for barium chloride
No,
because I'm
no,
seeing
no, no, no,
about
no, no, no,
100
no,
and
no. I'm
something
sorry for
add
the
to it, so that
misconception.
number is ridiculous.
No, I'm sorry for the misconception. Sorry, I was saying because I use four significant figures for barium, I was going to use four significant figures for chlorine, which would and to that to four significant figures for chlorine would be 35.45, and
Mm.
twice that amount would be 70.9 since you have two chloride molecules in BaCl2. When you add everything together now, you're supposed to get 137.3 plus 70.9. You're supposed to get that's a fraction 208.2 grams.
Point two.
So 208.2 grams, 208.2 grams.
All right.
So
So
now this is basically telling us that mhm, one
continue
mole,
talking. I'm just writing.
yeah, 1 mole of BaCl2 is equal to 208.2 grams. Now
Mm-hmm.
we're going to find how many moles are x moles in 0.521 grams. So x moles of
So then we're going
BaCl,
cross multiply, right?
yes, basically. It's a point broke. Me when that happen, it just
Getting distracted again, Owen. Boy.
it's a point
So
broke.
8.2 grams multiplied by the number of moles of BaCl2, right,
Mm-hmm.
is equal to basically 1 mole
Mm-hmm.
times 0.521 grams, right?
Yes, ma'am.
What are we
So
going to divide by?
we're basically going to divide by, you're going to divide 208, going to divide the 208.2 grams. Oh, sorry, let me say something. No, you're going to be dividing the 0.521 grams by 208.2 grams.
Okay, very good. So that cancels that. What's your answer?
5.521 divided by, what's that word? What's that number?
208.2.
Big fraction that is. Alright. This is going to be, I'm tempted to give it to you like that, you know. I'm coming.
The number
It's
looks
it's
weird,
it's
but it's not wrong.
no, it's in 60 it's in what? It's in scientific notation, and I didn't want to
Yeah.
give it in scientific notation.
Yeah, you need to give it to me in scientific notation.
Alright, it's going to be
That's fine.
2.5. It's going to be 2 point to significant configure maybe it is to 2 6 fig. So
Uh-huh.
2 to 3 6 fig, sorry. So it's going to be 2.50 times 10 to negative 3.
10 to the minus 3. All right, great.
Mm-hmm.
So we know that. Let me just put a highlight here so I can find it easily when I need it or when we need it, right?
Mm-hmm.
Now, the mass of water was 0.09 grams. So how many moles would that be? So basically 1 mole of water, right? H2O is equal to what?
18 grams.
Very good. So 0.09 grams of water is how many moles?
We're going to divide 0 point, you know what? You know, that's not a question like that. Anyways, what you're going to do is you're going to cross multiply. And when you cross multiply, you're going to get that. You're going to get 1 mole H2O that OZ that 0.09 is equal to mhm, is equal to the NHH2 dot 18 grams like that. Then you're going to divide everything by 18 grams. So that's going to be what?
Mm-hmm.
Divided by 18. Yeah. 5 times 10 to negative 3.
What was that?
But it's going to be 5 times 10 to negative 3 moles. So there are 5 times 10 negative 3 moles in 0.09 grams of H2O.
Very good. And remember, I was telling you that you can know if your answer is correct. If you use the formula, number of moles is equal to the mass of the substance. That's how we ended up with the 0.09 at the top, right?
Yes,
because that's the
ma'am.
mass of the substance divided by the molar mass of whatever you're trying to find, right? I want this to be engraved in your mind now because that's going to help you to work out the rest and not be confused. Okay?
The mass? Wait,
No, the formula.
the formula. You want me to learn how to use the formula?
I don't want to, you know how to use the formula because you know how to do moles. I want you to remember the formula now. Never ever taught you the formula because I wanted you to understand the concept. I need you to know the formula now.
Understand the formula. Let's still understand the concept. That's something why you. I don't want to use. I don't want to become depending on the formula. Like this is only the formula what we don't want to use. Me like me want to stumble upon a question and understand what me I do. Me no want to learn the formula for it.
But you already know the concept. That's what I'm telling you. You know the concept, so it's time for you to now know the formula. You don't have to use the formula if you don't want to use it because you still know how to do moles. I taught you how to do moles, right?
Yes, you did.
Yes, so if you can't do moles after you learn the formula, I'm going to conk you.
That's that's why we don't want to use the formula. I just want to steal the concept. You hear what I mean? No, this like only formula we don't want ever have to use. Like we don't want to use it. Only formula we don't
I'm not
want to
telling you
use.
to use it in a ON. I'm telling you to know it. There's a difference. Know it and using it is two different things. Because I can know how to use a spoon, but still try to use a fork to drink spoon. To drink soup.
True. You know what? I'm going to try to remember. You know, if I have to write a definition, that's the only time I'm going to use the formula. If I have to write a definition.
It's not hard to remember, you know, because you always end up with the same formula whenever you do the cross multiplication thing. You realize you still end up with the mass of the substance over the molar mass.
Well,
Number of moles is equal to that. Yes, miss.
It's going to be moles. It's going to be what? If we cross multiply, it's going to be what?
If when you cross multiply, you end up with number of moles on this side, right? Being equal to the mass of the substance, which was 0.09 grams. That's the mass of water we got, right? Over the molar mass of water, which is 18 grams. You see that?
Oh, so it's going to be mole. It's going to be mole over grams.
So the number of moles ON is equal to the mass of the substance that we got, 0.09. That's the mass of the substance over the molar mass. So basically, number of moles is equal to small m over big M.
So that's going to be basically that's what. It's a molar mass, right? So that's going to be gram per mole, not true?
Yep.
So that means what you're telling me, right? Down there, so the 18 grams, that is what is 80. Is supposed to be 18 grams per mole. Yeah, that. Oh, that. Okay.
And then because it's per mole on the underside of the bar, it will just become mole, right?
Yeah,
So that's how we got moles.
Yeah. When you multiply, it will come up. When you multiply and change the sign and everything, when you reciprocate, it will come up and change. It will change from division to multiplication. So
Yeah.
essentially, only thing you have a work with are just moles. Everything, every unit here.
Because grams cancel grams. So you see how we get that now from, so you see how the formula relates to this thing? It's the same formula. I just never told you that it was the formula.
Yeah. I'm going to remember it when I have to write a definition.
Okay. That's fine with me. That's fine with me. We can continue now?
Yes, we can.
All right. Let me just rewrite this thing real quick. So we had BaCl2.xH2, correct?
Yes, ma'am.
Heat was applied and we got the anhydrous salt, which is BaCl2, and we also got some number of moles of H2, right?
Yes, ma'am.
For H2O, we got 5.0 times 10 to the minus 3 moles, right?
True.
And we got what?
2.50 times 10 negative 3 for the, yeah, 250.
Now, how would you find the mole ratio for this? The simplest ratio, that is.
I wish one of them smaller. You're going to divide everything by 2.5 times 10 negative 3.
Very good. So you divide everything by the smaller number.
This is why I don't like using the standard thing on my calculator. Every time I use it, it tells me error. I'm hate it.
That means you now use a calculator properly.
So
The
you're
next,
going to help me. You're going to help me today. So I know it's going to be what?
all
2
right.
is going to 2.5.
Put it
This is
in
going to
brackets.
be
It's easier to use when you put it in brackets, okay? The
what do you mean?
entire number. The entire number, put
Okay,
a
put
bracket.
everything.
Let me see if
I
I
use
can
my
pull up a calculator real quick. I need to download the scientific calculator on my laptop because I can't deal with this thing here. So, all
buddy,
right,
you
this.
see?
All right, put
Mm-hmm.
a bracket. You're seeing this, right?
So bracket, yes, ma'am.
2.5, right?
Wait, we're gonna use 5.0. Cause when we divide 2.5, we don't say we'll get 1. We're gonna use
All right,
5.0.
let's do that one. 5.0.
Mm-hmm. 5.0.
I don't even think exponent thing. Jesus Christ.
Mm-hmm.
That's not it either. I don't know how to use this in a 5.0.
Sit over
Oh,
there,
and
sir.
I think it's the
Sit over there,
EXP
sir.
thing.
The 10, no, over there, sir. Sit over there, sir. 10.
No, this I thought it was this, but it raised the 5 to it raised the 10 to 5.
Oh.
Let me test if this is it.
The E
Not at
something supposed to
all.
be something for natural log for E. Something not
I
no.
know that's a natural log. Oh my god. All right,
It's
let me
supposed
try
to
the
be
times 10
natural
to the
log.
thing again. That's a binary theorem. All right,
EXP. No, use EXP. Exponent. Use EXP.
that's why I did.
Oh, okay.
And
Alright then. It look weird though, honestly.
yeah, no, it's not that. That's not it. Or am I being an idiot and not using it properly? Oh my god. All right, you know what? Let me look. Let me Google a scientific calculator.
Use Mathway.
What? Mathway?
Mathway.
Mathme.
Mathway, yeah.
That's what I said first. Yes. Oh, teacher. Okay.
We not here, sometimes you're really low.
Oh. All right.
There you go.
So, my god. All right. 5.0. Wait. Oh, teacher, times 10, right?
Mm-hmm.
Why is this thing doing this to me?
Go back out.
Yeah.
Mm-hmm.
You know
Type
what?
it.
I'm stressed. 5.0 times 10
Mm-hmm.
to the minus 3, right?
Yes, -3, yeah.
Divided by, and then
You
put the
know,
next number
at
in
least we
the
can
bracket.
bother us. I'm coming.
Which was 2.5 times 10 to the minus 3 as well.
Yes, ma'am.
If it were minus 2, you'd know that the minus 3 is bigger. The bigger the negative exponent, the bigger the number. The smaller the number, sorry. Okay?
So if it was -2, you know that -2 would be larger than -3. That yes, right?
Yeah.
Okay.
So if you had 5.0 times 10 to the minus 3 and
Mm-hmm.
2.5 times 10 to the minus 2, 5.0 times 10 to the minus 3 would be the smaller number of the two, okay?
I say, would that be the smaller number?
Yeah, the 1 times 10 to the minus 3 would be the smaller number. I can show you how.
-3? Yeah, show me, show me.
2.5 times 10 to the minus 2 was what I said, right? This is literally, if you
Yeah.
write it out, it would be going back 2 spaces, correct? So it
Mm-hmm.
would be 0.025, right?
Mm-hmm.
And 5.0 times 10 to the minus 3 would be going back 3 spaces, so it would be 0.005. 1, 2, 3, correct?
True. That's smaller for true. That's smaller for true.
Yeah. So the further back you go, the more zeros you will have. So that's why it would be the smaller number, right?
Mm-hmm.
All right, so
It tell
that's
me syntax error. When me do it, it tell me syntax error.
what? Oh, yeah, convert to scientific notation if you can. Why this tell me 2 times 10 to the 0? That's 2, right?
Mm-hmm. 2 times 10, yeah, so it would be basically 1. It would basically be 2. So yeah,
2, miss?
yeah.
Yes.
2.
Yes, it's 2.
What this time is syntax error. This is something I like using, you know. You tell me syntax error.
I am honestly convinced that you're not using that calculator properly. Tell me exactly what you put into the calculator.
I put 5.0, I put 5.0 times 10 to negative 3. And the exponent, I use the exponent thing there, but when I do it, I didn't see the X thing come up, so I had to insert it myself.
Oh, wait. You put EXP,
Yeah.
then what?
I put the arrays, you know the thing
Oh,
when
don't
you write
raise it to anything. That's why you're getting the syntax error. When you put EXP, just put the number.
but not come up, it, like you literally just have 110 there. What am I supposed to use the 10 by itself to do? The thing not come up itself.
So when you put it in the calculator, this is not what comes up. It's not this. You get just 10.
I just get 10.
Yeah, put the number beside it. Don't raise it to anything. Just put the number beside it. Try that.
Yeah, alright. Negative 3. This looks like not gonna work, but okay.
If it don't work, put the numbers in brackets when you
It
put it
work.
beside it.
It
Okay.
work. It work, Cameo. It works. It works. It works. It works.
Yeah, don't raise the number. Like if it comes up just like the 10, just put the number beside it that you're raising it to.
It works.
Which one you're using, the Casio, right?
Yeah, I use Casio. If I
Yeah,
did
that's it.
sharp, it would look so.
Yeah,
I
it looks
can me
different in
sharp.
different calculators. So this is what you got. 5.0 time the times 10 came, it was multiplied the
So
multiplication
question,
sign.
if them get one whole number, like, if them get to raise to 2, me wouldn't put nothing there.
No, don't put anything. Don't put
Just
anything.
put
Don't
just put
raise
it
the number. Just
just
put
put
the
it beside
number
that
that
3
you raise it to beside it. Yeah.
in a bracket. You
You
say?
can put it in brackets. It should work still.
Don't put it in a bracket. This look away if it's true.
Test it and tell me if it works. I don't usually put it in brackets. I just put it in.
It look it just I'm putting in the brackets. It's time consuming to put in brackets, but I have to do it.
Can't believe so
It
we
no
spend.
work.
It no work if you just put it as is. Don't put anything beside it. Then just put the number beside it that you're raising it to. So this means that BaCl2 dot, we have 2 water molecules, 2 H2O, right? Because we got 1 to 2 for the mole ratio. This just means that X right here is equal to 2, and whatever would be, that would be 1 mole of barium chloride is, and 2 moles of water is formed. That would mean that this X right here is equal to 2, right?
Yes,
So
ma'am.
that would be the formula that we deduced. We have actually 7, 8, because we have a past paper question as well. But we're going to do one more, then cut the video so it's not too long, right? And then I'll just
Me got attempt to work out the one them on your worksheet. I mean, you have me can show you and send it and them how me work them out. If it makes sense to you,
you started, right?
huh?
You
No, me never
started.
started. No, I didn't start it.
Well, the worksheet that you sent to me had some working out on it.
Oh, that's what my class did. I didn't understand what they were doing in class.
Oh, so you understand this first part?
Yeah, I understand this first part. Wait, me on the document or on this we're teaching me right now?
What I'm teaching you now, miss?
Of course I understand it. Yeah, of course I know.
Yeah, go ahead.
So it says a 0.497 gram sample of chloride of a group 1 metal Z is dissolved in water. Excess acidified silver nitrate is added to the solution. The resulting precipitate is filtered and dried to constant mass. The mass of silver chloride formed is 0.957 grams. Deduce which metal is present in the original chloride. I'm supposed to. Okay,
All
now,
right.
so we're
First, ask yourself what you know, what you don't know, what you need to find out. What do we know?
we know that we basically know so we use we know so basically use one group 1 metal we know so basically use one group 1 metal chloride so HCl and we know so we use 0.497 grams of that group 1 metal chloride. feet. So we know, so we use 0.497 grams of ZCl
All
to
right,
make
let
up
me
with
write
something.
that
That
down.
makes sense to you what I said a while ago?
Yes, it was on
Okay.
point. You never make me have to ask you, so that's great. ZCl. So you know that you can deduce the formula because that would mean that Z is plus and Cl is minus. You know, we do the whole crossing thing. But since they're both one, we just put ZCl, right?
Mm-hmm.
Okay. So ZCl.
Mm-hmm. And then no, it says that it was dissolved in water. So
So
we know
it needs.
someone mixture in
So
our
what would be the
water.
state symbol for this?
This now would be aqueous.
Very good. And we didn't have to ponder whether it would actually dissolve in water because one, they told you that it would dissolve in water, and you know it would dissolve in water because all group 1 chlorides are soluble. All right.
Everything from group one metal is soluble. Everything from group one soluble.
All
Everything for is soluble. And
right.
then it says that it says that excess acidified nitrate is going to be added to it. This is what this is AgNO3, not true.
Very good. AgNO3. So AgNO3.
Mm-hmm.
State symbol, miss. Very
Aqueous.
good. Aqueous just means that it's able to dissolve in water. All right.
Yes, ma'am.
What else do we
Then
know?
we're going to be we're going this is gonna be one displacement something not true. This
Double
is gonna be one
displacement. Yeah.
double displacement reaction.
Mm-hmm.
That means that two things that displace each other. That you mean, right? So this means we'll get Z ZNO3
Very good. And
aqueous,
and
and we'll get AgCl. Okay, is this insoluble?
very good. So
That could be one
that's
solid.
very good. So that's a precipitate. So whenever we're doing double displacement
Pause,
reactions,
pause,
X will
pause,
get with this. The
pause, pause.
cation of one will get to with the anion of another, and the anion of the first one will get with the cation of the second, right?
Oh, what you just said a while ago? Come again, por favor?
Owen, I'm saying that whenever a double displacement reaction occurs, the cation of the first sample will get with the anion of the other, right?
Mm-hmm.
And the anion of the first will get with the cation of the second. So
Me
that's
just,
how we
me
got
just,
silver chloride and whatever first one, ZNO3, right?
you said something interesting a lot. You said double displacement. Yeah, single displacement and triple displacement reactions.
No,
So, okay,
it's just what it's called.
okay, okay. Okay, you
Single,
say.
single displacement. All right. Let me see.
I'm gonna
If
use
you
that stuff.
have metal reacting with an acid HCl, right?
Mm-hmm. Yeah.
You would get MCl, right?
Yeah, you get MCl and plus H2 gas.
Exactly. This H here is displaced. We just don't call it a single displacement
Now,
reaction.
what type of reaction we call this again?
This would be a neutralization, right? No.
No, no, that's
Nope.
with salt. That's what the acid
Very
neutralization.
good. Salt and acid. What would this be? Oh, one displacement reaction here.
It's not a displacement reaction, but you say you don't call it single displacement reaction.
No, we just call it displacement.
Okay.
This is a grade 11 stuff, don't?
Yeah.
Yeah.
Then you have
And you have
redox reaction.
combination and redox. Very good. You
I
have
don't know combination.
combination.
Probably know what a combination reaction, but me no
You
remember
know
what
what
it
a
looks like.
combination reaction is? Let me tell you for a fact. A combination is like A plus B give you AB, right? So an
Oh.
example of this would be let's say, wow, all right. If you react hydrogen gas with chlorine Hg plus Cl gas, Cl2 gas.
Yeah, get HCl.
Very good.
Well, you're supposed to put one, two. Yeah, you have to put one, two on that. Yeah, I want that to be that.
Yeah. So
Yeah,
that's
one
a
next one. The one we know all the while when we burn something.
combustion
Decomposition
reactions.
reaction. Yeah, no man, the composition reaction. Yeah, and composition
Oh,
reaction.
when you
Break
apply
down
heat,
something. Yeah, you break it down, you know? Yeah.
yeah, that's a decomposition reaction. You have chemical decomposition reactions, but I'm not getting to that.
Let us not.
So back to this. So we know the
Yeah.
products that we got. Now we know that the mass of silver chloride that we got was what? This?
0.497 gram. Wait, you not put it, you not be thinking of it in the order, you know? Alright.
Oh, sorry. So the sample of this was 0.497 grams. Great. All right. So now what do they want you to find?
They want me to deduce which metal is present in the original chloride.
Yeah. So what we wanted to know is find out the mass of the chloride ions present in the sample of ZCl, right?
Mm-hmm.
And how would
Alright,
we?
that means that we can subtract. We can basically subtract. We can them bigger. We can basically subtract the 0.497 from the 0.97 to find how much of the chloride was in it.
No,
No, that's what that's
there
how
are
it
two
works.
different compounds, completely different compounds. Silver chloride and ZCl, right? Which is a group one.
Mm.
So they don't have the same compositions for one. That's why you can't just subtract like that.
Alright. That makes
Because
sense.
AgCl is not in ZCl, the ZCl sample. Or at least we don't know that. We don't know what is in the ZCl sample. We don't know if it's just ZCl or it has ZCl and something else, right?
Mm-hmm.
But
But I
what we
think it's
do
safe.
know?
But I think it's safe to assume it only has the Z in it because they told us so up there. So I want group one metal.
I guess, but you still don't know.
True.
You still couldn't find it out like that anyway.
True.
You'd
So
you'd
what
end up at
can
a
we
dead
do?
end. That's
True.
what I am
So
asking you.
me I look on it, what me can do? Me know if you have facts so me can find the number of moles and me use like 0.597. That's if I want
Yeah,
sure for
0.97 miss.
0.5 the 0.957 grams of HCl
Yeah, we
solid.
can do that.
But
Yes,
that
we
alone
can do
now
that.
but that alone now go help with do something else.
Exactly. So how does that AgCl relate to the ZCl based on the equation?
How does what? The ZCl relate to the HG cell?
Mm-hmm.
Alright, I know for a fact they both of them contain in Cl.
Yeah. What else
That's
do we
one.
know about them?
We know the masses of both of them.
Yeah, but that not help we. Tell me
True.
something we're gonna help we. Remember, let me give you a little hint. Remember, we usually deal
Yeah.
with mole ratios because,
Mm-hmm.
that is more useful than masses.
Alright, so if that be the case, we can basically find the mole ratio of both of them, or we can basically find the mole ratio of both of them.
And what's the mole
No,
ratio?
but we couldn't use the mole ratio because we have grams here, so
Look at the equation, Owen.
oh, 1 to 1, everything reacts 1 to 1.
Yes, miss, 1 to 1. So that means whatever mole of AgCl you get is the same number of moles of ZCl. And if we find that out, how can we find the mass of the molecular mass of the Z?
1 second, 1 second, 1 second.
Mm-hmm. Oh my.
So if you work out the
Yeah, sorry. What was that? All right. Let me repeat the question since you're back. All right. The last question I asked you was, now that we know that the thingy ZCl reacts in a 1 to 1 mole ratio. If one mole of ZCl reacts with, you know, AgNO3 to produce 1 mole of AgCl, right?
That's true.
That would mean that whatever number of moles we get from the AgCl would be equal to the number of moles in ZCl, right?
That is true.
How can we use that information to find out the molecular formula mass of ZCl and ultimately the mass of the molecular mass of, you know, Z to identify the what compound Z is?
Just a quick recap in class. What's the difference between the empirical and the molecular formula?
The empirical formula mass would be the simplest mole ratio. All right, so let's say you have for what are these called? Carbohydrates, right? Their empirical formula is CH2O, right? So the empirical formula mass of this would be 12 plus 2 plus 16, right? For glucose, though, it's C6H12O6, right?
Yeah.
The molecular formula mass, on the other hand, now would be 6 times 12 plus 12 plus 6 times 16, right?
Yeah.
So this here would be your empirical formula mass, while the bottom one here would be your molecular formula mass.
Oh, so the simplest form. So you're basically telling me, so you want a molecular formula, so you want individual, well, you basically want to know the
Yeah,
individual elements, the amount of the total amount. How will you put that together?
calm
Because
down. Don't get flustered. Don't get flustered. If you
because
get flustered, you'll have a harder time. All right?
yeah. So you're basically telling me you want to know how many of the Z element is in the chloride molecule, or
The
is in the
ZCl.
ZCl sample, and you want to know how many Cl.
Once we find that
Really,
out, you know, once we find that out, we already know it's Cl, so we can easily subtract. If we find the molecular formula mass of ZCl, we can easily subtract the molar mass of Cl from the compound and get the molar mass of ZCl. Sorry.
I go
You
work the
understand what I'm
13
trying to say?
steps.
All right, no problem. So
No,
this
yes,
is where we left off.
we're gonna work out in our steps. We're gonna work out in our steps, and we'll figure. Oh yes, along the way.
No problem. No problem at all. All right, so we have everything we need to know from the equation, the question written out already, right?
That's true.
Now we need to find out the number of moles of AgCl in 0.957 grams, right? So 1 mole, we're doing it like this. 1 mole of AgCl is equal to what?
Welcome.
No problem. Silver is over
You know,
here.
some nowadays a silver or two.
108.
Where use 4 significant figures or 3?
It don't really matter. It don't really matter in this at this point in time. It don't really matter. Okay, you're gonna get the same answer anyway. Just use sufficient sufficient amount of numbers. And
107.9 grams. And then no X more.
what was that? What you get for the molecular mass of AgCl?
What am I using for its mass? I'm using 107.9 grams.
Add the chlorine atom and tell me now. Chlorine is 35.5.
Malcolm. 107.9 plus 35.45. That is going to be equal to 143.35. If me I use 3 to think 143.4
grams. And we know that we have 0.957 grams in the sample, right? So how many moles would that be?
That is going to be equal to it's just going to be when we cross multiply, it's going to say 0.957 divided by 143.4.
Very good. So that's the mass of the substance over the molar mass is equal to the number of moles. What's the number of moles that we got?
I'm coming, give me a second.
No rush.
That would be to 36 figure 6.67 times 10 negative 3.
Very good. So that's the number of moles of AgCl that we got, right? With this information, we now know that, let me move this over a bit. We now know that 6 point whatever number of moles of AgCl would be equal to the number of moles of ZCl, right?
Yes, because they're like in a 1-to-1 mole ratio.
Very good. So what we know about this now is that 0.497 grams of ZCl, right, is equal to 6.67 times 10 to the minus 3 moles. You seeing that?
Yes, I see that.
Because that's the mass of ZCl in the sample. So you see why we could have just subtract like that now?
Yeah, Mr. We can just subtract like that. No, but two different something.
So now,
They're completely different in their chemical composition, so we just couldn't do that.
exactly. So now we need to find out now the mass in 1 mole of the substance, right?
That would make
so
sense.
1 mole of ZCl. So do the cross multiplication and tell me.
Yeah, don't. Oh God. Anyways, when you cross multiply, we'll get mass 6.67. So that means that we're supposed to divide with Neko. So we have to divide the 0.497 by the 6.67 times 10 to the negative 3.
Very good. And that would give us how much the 1 mole of the substance is, the mass of 1 mole of the substance, right?
That's true. Not forget it, man. Come plug it in. Alright. So I have plugged in my laptop. I can go back to the calculation thing on my calculator. So that is going to be 0.497 divided by 6.67. Remember kita lasting there, you tell me foolishness. Exponent negative 3 close bracket. This is what, to three significant figures, 74.5 grams.
All right, so we know that ZCl now, 1 mole of ZCl is equal to 74.5 grams, right? Now, how would we find the mass of Z only?
All right, so you know that the total amount of mass of ZCl is 74.5 grams. Now you also you know that chemically this substance is chemically composed of Z and Cl. You know the mass of Cl, so you could subtract the mass of Cl from the 74.5 grams in order to find out what Z would be.
Very good. So what we know, the molar mass is literally the mass of Z plus the mass of chlorine, right? The chlorine atom, which is equal to the mass of Z, which we don't know, plus 35.5 grams, right? And all of that would be equal to 74.5 grams. Seeing that? Owen?
Yes, ma'am.
Okay, because I'm wondering. All right.
I'm here, I'm seeing it.
Okay. So 74.5.
I'm seeing it.
I heard
I'm
it.
not.
I think we have a delay. That's the problem.
My internet was unstable for me. That's why I didn't hear me for a while.
Oh, that's fine. So we would subtract, right? As you said. And what would we get?
Okay. 70, 39. 39 grams. So you know that's going to be potassium. Hey.
So therefore, very good. So the mass, therefore, Z is potassium. All right? That clear?
All right. Yes, ma'am.
All right, so I'm going to cut the video now and we do the rest of the problems.